Neural networks are one of the most powerful learning algorithms that we have today. In this and in the next few videos, I'd like to start talking about a learning algorithm for fitting the parameters of a neural network given a training set. As with the discussion of most of our learning algorithms, we're going to begin by talking about a cost function for fitting the parameters of the network. I'm going to focus on the application of neural networks to classification problems. So suppose we have a network like that shown on the left, and suppose we have a training set like this of xi, yi pairs of m training examples. I'm going to use uppercase L to denote the total number of layers in this network. So for the network shown on the left, we would have capital L equals 4. And I'm going to use S subscript L to denote the number of units, that is the number of neurons, not counting the bias unit in layer L of the network. So for example, we would have S1, which is the input layer, has 3 units, S2 in my example has 5 units, and the output layer S4, which is also equal to SL because capital L is equal to 4, the output layer in my example on the left has 4 units. We're going to consider two types of classification problems. The first is binary classification, where the labels y are either 0 or 1. In this case, we would have one output unit. So this neural network on top has 4 output units, but if we had binary classification, we would have only one output unit that computes h of x. And the output of the neural network would be h of x is going to be a row number. And in this case, the number of output units SL, where L is again the index of the final layer, because that's the number of layers we have in the network. But so the number of units we have in the output layer is going to be equal to 1. In this case, to simplify notation later, I'm also going to set k equals 1. So you can think of k as also denoting the number of units in the output layer. The second type of classification problem we'll consider will be multi-class classification problem, where we may have k distinct classes. So our early example had this representation for y if we had 4 classes, and in this case we would have capital K output units, and our hypothesis will output vectors that are k-dimensional, and the number of output units will be equal to k. And usually we would have k greater than or equal to 3 in this case, because if we had 2 classes, then we don't need to use the 1 versus all method. We need to use the 1 versus all method only if we have k greater than or equal to 3 classes. So if we had only 2 classes, we will need to use only 1 output unit. Now let's define the cost function for our neural network. The cost function we use for the neural network is going to be a generalization of the one that we use for logistic regression. For logistic regression, we used to minimize the cost function j of theta that was minus 1 over m of this cost function, and then plus this extra regularization term here, where this was a sum from j equals 1 through n, because we did not regularize the bias term theta 0. For a neural network, our cost function is going to be a generalization of this, where instead of having basically just one logistic regression output unit, we may instead have k of them. So here's our cost function. Our neural network now outputs vectors in Rk, where k might be equal to 1 if we have a binary classification problem. I'm going to use this notation h of x subscript I to denote the ith output. That is, h of x is a k-dimensional vector, and so this subscript I just selects out the ith element of the vector that is output by my neural network. My cost function j of theta is now going to be the following, is minus 1 over m of a sum of a similar term to what we had for logistic regression, except that we have this sum from k equals 1 through k. This summation is basically a sum over my k output unit. So if I have 4 output units, that is, if the final layer of my neural network has 4 output units, then this is a sum from k equals 1 through 4 of basically the logistic regression algorithm's cost function, but summing that cost function over each of my 4 output units in turn. And so you notice in particular that this applies to yk hk, because we're basically taking the kth output unit and comparing that to the value of yk, which is one of those vectors saying what class it should be. And finally, the second term here is the regularization term, similar to what we had for logistic regression. This summation terms looks really complicated, but all it's doing is just summing over these terms theta, j, I, l for all values of I, j, and l, except that we don't sum over the terms corresponding to these bias values like we had for logistic regression. Concretely, we don't sum over the terms corresponding to where I is equal to 0. So that is because when we're computing the activation of a neuron, we have terms like these, theta I0 plus theta I1 x1 plus and so on, where I guess we could have a 2 there if this is the first hidden layer. And so the values with a 0 there, that corresponds to something that multiplies into an x0 or an a0. And so this is kind of like a bias unit. And by analogy to what we were doing for logistic regression, we won't sum over those terms in our regularization term because we don't want to regularize them and string their values to 0. But this is just one possible convention, and even if you were to sum over, I equals 0 up to SL, it'll work about the same, and it doesn't make a big difference. But maybe this convention of not regularizing the bias term is just slightly more common. So that's the cost function we're going to use to fit our neural network. In the next video, we'll start to talk about an algorithm for trying to optimize the cost function.